Hi, today I'm gonna teach you how to write your first machine learning algorithm in just 10 lines. So this tutorial is based on Python, and I would assume that you would know at least a little bit of Python, but if not, it's okay. Just try to follow along. It's the logic that's a lot more important, and Python's syntax is pretty easy to read, so at the very least you would still understand what's going on. So I'm going to divide this tutorial into two parts. So for part one, I'm going to give you a very quick overview of what machine learning is. The goal is to give you a conceptual and intuitive grasp of the topic. And then I'm also going to teach you how to train your machine learning model, the types of machine learning algorithms out there, and I'm also going to discuss in depth about multivariate linear regression, because that's the kind of algorithm that we will code for part two. For part two, I'm gonna teach you how to set up your coding environment in Colab, and then we'll go on to write your first machine learning algorithm in 10 steps. The data set that we'll be using is on predicting the UPDRS score in telemonitored Parkinson's patients. So I'm gonna discuss that in detail later on, so stay tuned. So what is machine learning? Let me explain it by comparing it to traditional computing. So in traditional computing, you tell a computer that, hey computer, this is how you should make this decision if this is the case. And if it's the other case, this is what you should do, and so on and so forth. But with machine learning, you can tell a computer that, hey computer, here are some labeled examples. Figure out how to predict similar data. So it's similar to this old adage of teaching a person how to fish instead of just giving a person fish. So it's like it's like teaching the computer how to be self-sufficient and how to make decisions on its own. So, formally, machine learning is about teaching a machine to learn by example and make autonomous decisions by using statistical data analysis. So, because of this, it needs huge amounts of data and powerful computing resources and learning from the data. Because if you don't feed it a lot of information, it's not gonna make a very accurate model. So, why is machine learning a big deal? First, it's behind a lot of interesting technologies like self driving cars, tumor detection, gene sequencing, personal assistance, translations, object detection, and more. And then next, it can automate structured, repetitive tasks that used to require manual labor. And because of this, it could free up our time for tasks that require more creative and cognitive power. So, I believe that machines could never ever absolutely replace humans, but it could empower us by freeing up our time for higher level thinking, and for enabling us to do more because we have more resources on our hands. So how do you train a machine learning model? So first, of course, you have to have a huge data set. And since we're teaching the computer to learn by example, the data should be labeled. So it should contain whatever your inputs are and whatever the predicted values are. And then from this labeled data, you should split it into a training set and a test set. And you use your training set to train train your model. So this is where the computer makes like thousands of computations to find the optimal weights and parameters that would produce the least amount of error, and that would produce the best predictive value. And then you could test this model by using the labeled test set. You could compare the actual prediction from what the computer provided for you. And then, of course, machine learning, it's an iterative process, and you train and test several times until you're finally happy with your results. So there are two types of machine learning algorithms if you want to dissect them based on the kind of input data that you feed to the machine. So if you have labeled data or data that contains the supposed outputs of whatever you want your model to predict, then you could use supervised learning models. So in supervised learning, you train a model based on known input and output data, and then it finds some patterns between these two, and it uses these patterns to predict future outputs. So if your data doesn't contain any examples of the supposed output, then you could use unsupervised learning. So in unsupervised learning, the machine finds hidden patterns or intrinsic structures in the input data, and it comes up with the output data by itself. So even if unsupervised learning sounds a lot cooler than um, supervised learning, it's actually a little more difficult to do because you would need a lot more data for the machine to be able to, detect any small pattern. And then it's also usually just used for clustering and not really regression. So if you're doing regression, like usually like the standard practice, like at least as of now, is just doing supervised learning. So unsupervised learning is mainly used for clustering data. So these are the two types of machine learning algorithms if you want to classify them based on the kind of output that you want to produce. So if you want to predict continuous values or any real numbers, then you could use regression models. So some examples would be predicting the temperature tomorrow, the amount of rainfall that we would get next week, or the stock price of Apple 2 days from now. And then if you want to predict categories, or at its most basic case, binary outcomes, then you could use classification models. So examples would be, will it be hot or cold tomorrow? Is this tumor malignant or not? Or like what kind of pet is in the photo? Before we proceed, let's do a quick checkpoint to see whether you understood the concept or not. Hopefully you did. So, in these 5 examples, should you use regression or not? So, example number 1, predicting whether it will rain or not tomorrow. Number 2, deciding whether to buy or sell Tesla stock. Number 3, predicting the market price of a given apartment. Number 4, predicting whether a given plane ticket price is the lowest possible value or not. And then last, predicting what kind of pet is in a photo. Okay, so I'm pausing the video and just give yourself maybe around 60 seconds to answer the questions and just hit play again when you're done. Okay, time's up. It's time to check your answers. So, in the 5 examples, there's only one example of regression, which is number 3, predicting the market price of an apartment. So, the other examples, especially number 1, 2, and 4, are binary classification examples, like meaning they only have like a yes or no or true or false answer. So that makes it a classification problem and not a regression problem, since the outputs expected are not continuous. So today, for our coding example, we will be using multivariate linear regression. So it's basically just a model that could predict one continuous variable or real number based on multiple independent variables or attributes. So this is what the model looks like. So the inputs and the features are represented by the x's, and then the outputs and the predicted values of y are represented by h of theta of x. H here means the hypothesis. And then, so the unknowns of our model are the weights or the thetas. So these are the variables that the machine will solve for over a lot of iterations. So the objective of the model is to minimize the cost function or the error. So the cost function is computed at the end of each iteration to determine which direction to iterate the weights. So the regression model uses a gradient descent algorithm to find the optimal set of weights that would produce the lowest MSE. So it is an iterative process, and it usually does like thousands of iterations before it finds the optimal solution. So you could see that in the graph over here. So the y-axis is representing the cost, and then so it's like a so this is like a contour, right? So like you randomly like initialize the set of thetas from somewhere, and then based on the cost function you try to like iterate and move around the theta values until you find the optimal solution. So it's not always the case that you find the global or like the absolute best solution, because there are several troughs as you could see in here, and it's possible that it could settle in like a local minimum instead of like a global minimum. So another important parameter in this kind of machine learning model is the learning rate, or the alpha. So the alpha determines by how much the thetas should move at each iteration. So if the learning rate is too small, it would take you like a lot more iterations to arrive at like an optimal solution. But at the same time, if your alpha is too large, you could be like your steps could be so huge that you could be missing like the optimum solution, because like your steps are so huge. So even if we're doing linear regression, it's possible to add polynomial features. So in some data sets, the inputs are not linearly related to the outputs. So it's good to use polynomial features to let the model fit the data better. However, it is not useful in all cases, and it could lead to the model overfitting the data. So overfitting happens when models fit the training data significantly more than the test data. However, some slight overfitting is okay. It's even a little expected. And then, so even if we're adding polynomial features, the model still remains linear, because we're only adding exponents to the inputs which are known, and it's okay because it still makes the model linear, because the unknowns are the thetas, and as you can see here, they still remain linear despite the inputs having some polynomial degrees. This is Google Collaboratory, or Colab. So it's a free Jupyter notebook environment that requires no setup and runs entirely in the cloud. A lot of the common data science packages come pre-installed, so it's almost good to go. So with Colab, you could write, execute code, save, and share your analysis, and then also access powerful computing resources, all for free from your browser. Since it's part of the Google Suite, it works just like any other kind of Google document. So you could copy things to your drive, you could share stuff with your colleagues, you could like collaborate and work on the same document together. So it's really helpful in sharing your algorithm, writing some reports, and also working with other people for like data science projects. For your first machine learning algorithm, we will try to predict UPDRS scores in telemonitored Parkinson's patients. So Parkinson's disease is a degenerative central nervous system disorder. And in this study, patients were telemonitored remotely instead of having physical visits to reduce cost and inconvenience. And then from that data, clinicians tried to assign UPDRS scores. So UPDRS stands for Unified Parkinson's Disease Rating Scale, and it's used to classify the stage of the disease. So vocal impairment is the earliest indicator of the disease in 90% of the cases. And then there are two kinds of vocal impairments. First is dysphonia. It's when normal sound production is affected. And second is dysarthria. This is when problems with normal articulation of speech appear. So in this study, biomedical voice measurements from 42 people with early stage Parkinson's disease were taken. These people were recruited for a 6-month trial of a telemonitoring device for remote symptom progression monitoring. And then there are a total of 5,875 samples. So each patient has more than 100 or so measurements over the course of the 6-month trial. Okay, so before anything, let's try to import the libraries that we need. And if the version you want is not the one that's present, or if the library is not present, then just install it using this syntax above. And then next, let's load the data. So we're getting this data from the UCI machine learning repository. They also have lots of other machine learning data sets sorted by the kind of model that you want to use. So check it out also if you have time. So but for now, open the blue link, click the data folder, and then download the files and upload them to Colab. And then you can upload them in the files panel on your left. And then since it's a CSV file, we're loading it using pandas. And you can see a preview of the dataset below. And then next, we need to separate the input and output variables to separate data frames. So input data frame is X and output data frame is Y. So in here, there are two output variables, motor UPDRS and total UPDRS. But later on, we'll only need total UPDRS. So you'll still need to remove motor UPDRS later. And then next, you have to make sure that categorical variables are converted to binary variables. So we're making 1 column per subject, and the value should be 1 if it's the corresponding subject number and 0 otherwise. And then let's move on to the actual training part. So first, let's normalize the data. This isn't required, but this is good so that your model will be able to find the optimal parameters easier. And then next, let's add the polynomial features that we mentioned earlier. And then I did a lot of trial and error, and it seems like second degree works best, so put second degree here. So next we have to split the data set into a training set and a test set. So there's a preset function from sklearn called train test split, and we're just going to use that, but you have to specify the test size that you need. And then next, let's initialize the linear regression model, and let's train the model using the training set. So both of these functions are from the sklearn library. So all the magic happens in the background, and all you need to type are 2 simple lines. So now that you've trained the data set, it's time to test it. So we need to produce YPRED, or like the predicted outputs of the X data frames, and compare those predicted outputs to the actual outputs. So we'll do the actual comparing in the next slide. So now let's talk about the performance metrics. So there are 2 important ones. The first one is mean squared error, which is just like the average error squared, just so that there's no negative. And what you only need to remember is that it has to be as close to 0 as possible. And then next is the variance score, or the R squared. So it just So R squared is just a measure of like how perfectly the model fits the data. So you can see that here in the next slide. So an R squared of 1 would be like the perfect diagonal line in the middle. So as you can see, like these are pretty close. So on the x-axis is the actual score, and on the y-axis is the predicted score. So like the perfect score would be like if they would align, all of them would align in the middle, because that's when the actual score would equal to the predicted score. So now that we're finally done coding that model, let's try to interpret and analyze how we should use it. So remember that the patient number was used as an input. So this means that the model also learned each patient's UDRPS variability, and it's important that we remember that when we're using the model. So if we use that model to predict the UDRPS with the same patients, then the accuracy will be more or less the same, because it also factors in it also factors in the individual variability of all the patients in that study. So if you want to use the model with other patients, the best solution would be to retrain with the data of the new patients so that the model could learn their individual variability. And then since this probably isn't possible, or it might actually be a real constraint, then worst case should be that the output should be interpreted as a range plus or minus the minimum and maximum individual variability. It's not the best solution out there, but it's not so bad, and it's okay as a caveat if like there are no other options. Okay, now I'll give you some tips on improving your model. So first, you could add a validation set and use it to tweak your parameters. So right after training the data, you could come up with a list of maybe 3 to 5 sets of parameters, and then you could measure the performance of those sets of parameters against the validation set. And then once you've chosen the final set of parameters, you can test the final performance using the test data. So in machine learning, there are so many parameters involved and so many ways to construct your model. So that means that there are so many ways to tweak it and optimize the performance of your model. So this is a good way of doing it if like you have a longer time frame and um, you have enough data to be able to have a validation set. And then second would be to add more data. So machine learning does extremely well if there's enough data, just because there are so many parameters and variables involved. So the machine needs a lot more data so that it could detect even the faintest patterns out there in the data. And then last would be to consult a neurologist and collaborate with him or her on engineering the features. This is so that we won't do like the brute force feature engineering that we did earlier when we um, set the polynomial features to the second degree. So what an expert could do would be to, just like list down which of those features are helpful, which of those features would be good to like, to see as a combination, to see as like combinations, because like some of those variables are not very independent. So like for variables that are dependent on each other, it would be good to combine those. And then there are also some variables that have like an exponential effect on the output. So like the experts would know which variables are those, and they could you could assign higher degrees for those particular variables. That concludes our tutorial for today. I hope you learned a lot, and I hope you would now be able to create your own machine learning models on your own.